To calculate the branch circuit rating for multiple motors on a single feeder, we must consider the full load amps, or FLA, of each motor. For question 1, we have three 480 volts 3-phase motors. Motor 1 has an FLA of 20 amps and a locked rotor amps, or LRA, of 100 amps. Motor 2 has an FLA of 25 amps and an LRA of 125 amps. Motor 3 has an FLA of 30 amps and an LRA of 150 amps. To determine the branch circuit rating, the National Electrical Code (NEC) requires us to size the conductors to at least 125% of the largest motor's FLA plus the sum of the other motor's FLA values. In this case, motor 3 has the largest FLA at 30 amps. Therefore, we calculate 1.25 times 30 amps, which equals 37.5 amps. We then add this to the sum of the other motor's FLA values, which is 20 amps plus 25 amps equals 45 amps. So, 37.5 amps plus 45 amps equals 82.5 amps. This means the minimum branch circuit ampacity must be 82.5 amps. Consult NEC Table 310.16 to select the appropriate conductor size based on the ampacity and the conductor's temperature rating. For overcurrent protection, we need to determine the maximum allowable circuit breaker size. The NEC allows for overcurrent protection devices to be sized based on the LRA of the largest motor. If using an inverse time circuit breaker, the maximum allowable size is typically 250% of the largest motor's FLA. For motor 3, 250% of 30 amps is 75 amps. We then add the FLA of the remaining motors. 20 amps plus 25 amps equals 45 amps. Therefore, 75 amps plus 45 amps equals 120 amps. The standard circuit breaker size above 120 amps is 125 amps. So, a 125 amp circuit breaker would likely be suitable. However, it's important to verify that this size will allow the motors to start without tripping the breaker. For short circuit and ground fault protection, the goal is to protect the conductors and equipment from damage due to fault currents. The overcurrent protection device, in this case the circuit breaker, should be able to interrupt fault currents before they reach dangerous levels. The settings should be coordinated with the motor's thermal overload protection to ensure that both short circuits and overloads are adequately addressed. Consult NEC Section 430 for specific requirements. For question 2, we have two 240 volts single-phase motors. Motor 4 has an FLA of 10 amps and an LRA of 50 amps. Motor 5 has an FLA of 15 amps and an LRA of 75 amps. These motors are connected to a common set of feeders, but each motor has its own circuit breaker. For motor 4, the branch circuit rating is determined by multiplying its FLA by 125%. Therefore, 1.25 times 10 amps equals 12.5 amps. This means the branch circuit conductors for motor 4 must have an ampacity of at least 12.5 amps. Similarly, for motor 5, we multiply its FLA by 125%. So, 1.25 times 15 amps equals 18.75 amps. The branch circuit conductors for motor 5 must have an ampacity of at least 18.75 amps. Again, consult NEC Table 310.16 to determine the appropriate conductor size. For overcurrent protection of motor 4, we can use a similar approach to the 3-phase motors. If we use an inverse time circuit breaker, we can size it up to 250% of the motor's FLA. Thus 2.5 times 10 amps equals 25 amps. The NEC also has a maximum value for overload protection, which must be considered. For motor 5, we do the same calculation. 2.5 times 15 amps equals 37.5 amps. Again, the NEC maximum overload protection value must be observed. Short circuit and ground fault protection for each motor should be provided by the individual circuit breakers. These breakers should be sized to protect the motor branch circuit conductors and motor windings from fault current. The settings must be coordinated with the motor's thermal overload protection. The common feeder supplying both motors must also have short circuit and ground fault protection. This protection should be sized to protect the feeder conductors from fault currents. The size of the feeder protection device is generally based on the sum of the branch circuit protection devices. However, the NEC provides specific rules for sizing feeder protection based on the type and size of the motors being served. For question 3, we have four 460 volts, 3-phase motors. Motor 6 has an FLA of 30 amps and an LRA of 150 amps. Motor 7 has an FLA of 35 amps and an LRA of 175 amps. Motor 8 has an FLA of 40 amps and an LRA of 200 amps. Motor 9 has an FLA of 45 amps and an LRA of 225 amps. These motors are connected in a group and fed by a single set of feeders with a common circuit breaker. To calculate the branch circuit rating, we take 125% of the largest motor's FLA and add the sum of the other motor's FLA values. The largest motor is motor 9 with an FLA of 45 amps. Therefore, 1.25 times 45 amps equals 56.25 amps. The sum of the other motors' FLA values is 30 amps plus 35 amps plus 40 amps, which equals 105 amps. Thus, 56.25 amps plus 105 amps equals 161.25 amps. The minimum branch circuit capacity is therefore 161.25 amps. Select the appropriate conductor size based on NEC Table 310.16. For overcurrent protection, we again size the circuit breaker based on the largest motor's FLA and LRA. The maximum allowable circuit breaker size is typically 250% of the largest motor's FLA. In this case, 250% of 45 amps is 112.5 amps. We then add the FLA of the remaining motors, which is 30 amps plus 35 amps plus 40 amps equals 105 amps. So, 112.5 amps plus 105 amps equals 217.5 amps. Choose the next standard circuit breaker size above 217.5 amps. For short circuit and ground fault protection, the overcurrent protection device must be able to interrupt fault currents before they reach dangerous levels. The settings should be coordinated with the motor's thermal overload protection. It's important to note that these calculations are simplified examples. Always consult the NEC and lookup codes for specific requirements and to ensure that the electrical installation is safe and compliant. Overcurrent protection is essential for electrical safety. It safeguards electrical circuits from excessive current, preventing overheating and potential fires. It works by automatically interrupting the circuit when the current exceeds a safe level, protecting both equipment and people. Overcurrent can arise from various causes. Firstly, short circuits occur when there is an unintended low resistance path in a circuit, leading to a surge of current. Secondly, overloads happen when a circuit is forced to carry more current than it's designed for, often due to too many devices operating simultaneously. Thirdly, ground faults occur when current leaks from an energized conductor to a grounded surface, such as a metal enclosure. These conditions can damage equipment, pose fire hazards, and endanger personnel. Overcurrent protection devices come in different forms. Firstly, fuses are one-time use devices that melt and break the circuit when the current exceeds their rating. Secondly, circuit breakers are resettable devices that trip and interrupt the circuit under overcurrent conditions and can be manually reset after the fault is cleared. Thirdly, thermal overloads are designed to protect motors from overheating due to prolonged overcurrent by tripping the motor circuit. NEC Articles 240 and 430 provide detailed requirements for overcurrent protection. NEC Article 240 covers the general requirements for overcurrent protection of conductors and equipment, including fuse and circuit breaker ratings, interrupting ratings, and location requirements. NEC Article 430 specifically addresses the protection of motors, motor circuits, and motor control equipment, including overload protection, short circuit protection, and ground fault protection. Understanding these articles is crucial for ensuring electrical safety. Selecting the right overcurrent protection devices involves several considerations. Firstly, determine the circuit's normal current carrying capacity to establish the base for protection. Secondly, choose a device with an ampacity rating that matches or slightly exceeds the circuit's capacity, providing a safety margin. Thirdly, verify that the device's interrupting rating is sufficient to handle the maximum fault current at its location, preventing device failure during a fault. Fourthly, coordinate the protection devices to ensure that the device closest to the fault clears it first, minimizing disruption to the rest of the system. Lastly, consider the specific application and environmental conditions to select the appropriate device type and enclosure. Proper coordination of overcurrent protection is essential. Firstly, it involves selecting devices with time current characteristics that allow the downstream device to trip before the upstream device during a fault. Secondly, it prevents unnecessary outages by isolating the fault to the smallest possible area. Thirdly, it improves system reliability and minimizes downtime. Coordination studies use time current curves to analyze device performance under various fault conditions. Several methods are used for overcurrent protection. Firstly, time current curves graphically represent the tripping characteristics of overcurrent devices, aiding in coordination studies. Secondly, short circuit studies analyze the magnitude and duration of fault currents to ensure devices have adequate interrupting ratings. Thirdly, protective device coordination software automates the coordination process, streamlining device selection and settings. Regular maintenance and testing are critical. Firstly, inspect devices for damage, corrosion, and proper installation. Secondly, test devices periodically to verify their functionality and calibration. Thirdly, keep records of maintenance and testing activities to track device performance and identify potential issues. Staying current with NEC requirements is essential. Firstly, electrical codes and standards are regularly updated to reflect new technologies and safety practices. Secondly, electrical professionals must stay informed about these changes to ensure compliance and safety. Thirdly, resources such as training courses, industry publications, and professional organizations can help stay up to date. Ensuring electrical safety is a shared responsibility. Firstly, qualified electricians should perform electrical work and overcurrent protection design. Secondly, building owners and operators should maintain electrical systems and ensure regular inspections. Thirdly, everyone should be aware of electrical hazards and report any safety concerns promptly. By following best practices and adhering to safety standards, we can create a safer electrical environment for all. Consider additional resources such as the Electricaferu website, which offers a wide range of articles and tutorials on electrical engineering topics, including motor calculations and overcurrent protection. Also, the ECM Web website provides articles and resources for electrical professionals, covering topics such as overcurrent protection for multiple motors. Finally, the Schneider Electric website offers information on short circuit and ground fault protection for motors, along with other electrical products and solutions. These resources can provide valuable information and insights for electrical professionals and anyone interested in learning more about electrical safety and best practices. The calculations presented here are for educational purposes and should be verified by a qualified electrical engineer or electrician before implementation. Always refer to the latest edition of the National Electrical Code, or NEC, and local codes for specific requirements. Electrical work can be dangerous and should only be performed by qualified personnel. Firstly, always de-energize circuits before working on them. Secondly, use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. Thirdly, follow lockout/tagout procedures to prevent accidental energization. Fourthly, double-check all connections and terminations to ensure they are secure. Lastly, test the circuit after completing the work to verify proper operation and safety. By following these safety precautions, you can minimize the risk of electrical shock and other hazards. Remember, safety is always the top priority. Understanding motor calculations and overcurrent protection is crucial for electrical engineers and technicians. Firstly, it enables them to design safe and reliable electrical systems. Secondly, it ensures the proper operation and protection of motors and other equipment. Thirdly, it prevents electrical hazards and minimizes the risk of fire and injury. The National Electrical Code, or NEC, is a comprehensive set of standards that provides guidance on electrical installations and safety. It covers a wide range of topics, including motor calculations, overcurrent protection, grounding, and wiring methods. Familiarity with the NEC is essential for anyone working in the electrical industry. Several online resources are available for further learning. Firstly, the Electric Cafe website offers articles, tutorials, and calculators on electrical engineering topics. Secondly, the ECM website provides news, articles, and resources for electrical professionals. Thirdly, the Schneider Electric website offers information on electrical products, solutions, and technical support. Lastly, the IEE website provides access to technical publications and standards related to electrical engineering. These resources can help you stay informed and expand your knowledge of electrical engineering principles and practices. In summary, motor calculations and overcurrent protection are essential aspects of electrical engineering. By understanding the principles and following the NEC guidelines, you can ensure the safe and reliable operation of electrical systems. Remember to always prioritize safety and consult with qualified professionals when performing electrical work.